Thank you, Professor May and the co-prepare for inviting me, for giving me this opportunity to talk about the topic of paleofloods in Himalaya. And the big picture you see in the background, the first slide, actually is 2013 large flood. I mean, it was the flood of the millennium, actually, that destroyed almost the whole, I mean, that changed the landscape of Ganga Basin and its mountain front for several, I mean, now we see that. And this picture comes from the headwater. And that's when I started working on, I mean, looking for the past flood records in various river systems of Himalaya. So I will be talking about my work, which has been done by various students and postdocs in various parts of India, from Ladakh and northeastern part of the Himalaya. So you see the whole background of this, besides what we see in Himalaya, you can see that in the global flood risk record, you see that large part of the global south actually is more affected by the flood adversaries. And you see, this is actually confirming the brand line, which says that large part of the global south is not empowered. We are not getting enough flow of database, knowledge base, and empowerment. And that's the reason you see the mortality regarding the flood. It's also limited or largely focused in the global south area. And the whole idea of developing this record is something that we should have some data, because most of the data comes from the United States and I mean European continent, and some from the China. And largely we do not have any data from the global south, where most of the population, global population, lives actually, and the landscape is actually under stress as when you see the anthropogenic impact. So this is the problem I'm trying to suggest, that this mortality and the fragility is basically the problem that relates to the hindered flow of knowledge and lesser empowerment in the global south as far as academic values are concerned. You see, that is the reason I just started picking up this mountain system, Himalaya, and this mountain actually supports somewhere around 20% of the global system, global population. That's because it has the river Indus, the river Ganga, the river Brahmaputra, the Yangtze, Amu Darya, and many or more like Irrawaddy and rivers from in Afghanistan. So you see, these 5-6 rivers actually support almost 20% of the global humanity. And anything that happens in these areas actually has potential to dent the global supply chains and economy. And that's where these areas are really important to be understood, as they support a big system of human and supply chains and economies. And you see that is, if you see the India, the last 120 years, the maximum number of average annual floods have occurred in India, China, Indonesia. So that is global south, actually Southeast Asia. And that's why I'm saying, in the present world of the global connectivity, we cannot actually choose to remain silent because of this fragility of the global support supply chain. And that's why the major questions, I mean, we as a geologist can always start understanding the natural conditions of these floods. So what is the natural climatic ramp that induces such kind of higher flood frequencies in Himalayan region? What controls the magnitude of Himalayan floods in Himalayan region? And where are the hotspots of erosion and large floods in Himalaya? So these are the three major questions I'll try to answer. And that is my basic motivation behind this talk. And the structure of the talk will go as like this: the flood disaster of the millennium, that is 2013 flood. And we took few of our students to map the damage elements of this flood. And then geology of damage, what controls this? What controlled this damage pattern? Then geological controls of the flood magnitude. and past records from Indus and Brahmaputra. I'll be talking the two floods from the two syntaxis regions. And one, Indus is of course operates in the hyper-arid systems, I mean rain shadow zone, and Brahmaputra largely operates in the monsoon dominant system. So climate controls on floods and human migration, probably there will be some lead on this, and erosional hotspots and exhumation, because we did some kind of provenance understanding. We developed some data on the provenance records of these flood deposits. And then finally, I'll conclude. So if we talk about Himalaya, you see that Himalaya it's a mountain system that developed due to the plate collision, and this is where the mountain chain is, and we have large foreland system. And because of this thrust fold belt development, it forms a particular type of a orography. You see in the lower panel, right panel, this is the area which I am targeting here. You see the black line is the geomorphic section. So this is mountain topography, and blue colored line is the rainfall profile. This is the SWOT profile developed using TRMM. And there are two physiographic transitions. One lies just above the main boundary thrust, and second lies above the main central thrust, from where the mountain starts picking up the topography. So this is physiographic transition one, and just above this you have first rainfall high, and the second rainfall high actually lies at the southern belt of southern mountain front. This is above the main central thrust. So you have two rainfall highs confirming the two topographic changes in the mountains. So this is how the whole mountain system looks like. This is the under thrusting plate, and you have a main Himalayan thrust. And because of the overriding thrust sheets that are transporting material southward, you have main central thrust, you have main boundary thrust, and you have Himalayan frontal thrust. And this is how it looks in the field. So talking about 2013 flood, you see, these are some of the images that were captured during our field trips just soon after the floods, and this few of them are from the internet. See, this bridge on the river Ganga is actually 60 meters above the riverbed, and it was flooded. And the most important thing to note is that the sediment density, and this actually the suspended load actually imparts to the density of the flood waters, and that actually helps in rolling around larger clasts. So that's how the erosivity of the river system increases. And you see, this is further upstream, and these are the 5 winding roads before the event. This is the picture before the event, and after the event, two of these were buried. So this was mapped to be around 29 meters of aggradation. So 29 meters of aggradation in one shot, in 2 days of flood, was actually generated in 2013. This claimed around 6,000 lives, and 200 million worth of economy was lost. And when we started mapping the area for the damage pattern, we found that around 3,000 landslides were activated or generated. Around 1,000 buildings government buildings were damaged, and whole lot of civil infrastructure which was developed over the years was actually failed, and we had to deploy the Air Force, army, to evacuate the people from the headwaters to the mountain front. So this is the basic understanding what we developed in 2013, and this really caught our eyes. You see in the left panel, these are the landslides we mapped. So in Bhagirathi Valley alone, we had around 1,034 landslides, and the important thing to note is these landslides are forming a certain clusters. So the one cluster is in the upper reaches, and second cluster is in the lower reaches. Likewise, the building damage, the first cluster in the upper reaches and second cluster in the lower reaches. So these are the two distinct clusters of landslides, as well as the building damage and the infrastructure. Now I'll come back to this image. This is the physiographic transition 1, over which the first cluster lies, and second physiographic transition, which is above the main central thrust. The second cluster lies. So this, when we see that how the rainfall, extreme rainfall interacts with the mountain system like Himalaya, there comes, I mean, in pictures, some sense of predictability. I mean, similar thing will happen when you will have an earthquake. These are the high topographic, high relief areas that interact in a way that they produce these damages. So in mountain system like Himalaya, the damage zones are really predictable. This is what the take-home message from so far the talk is, that damage zones in Himalaya, when the flood of 2013 event, I mean, magnitude strikes, these damage zones are predictable. And these are probably lying over the physiographic transitions where most of the rainfall actually, orography forms. And this is, again, you see, if you see the main Himalayan thrust, this is how the underlying plate, if you see the under thrusting plate, this is the geometry of the under thrusting plate, and it forms a ramp, and it's a flat and ramp geometry. So this is the ramp, and on just above this ramp, any material when it encounters the higher gradient system, it buckles up. And that's why on just above this ramp, you are finding the physiographic transitions. So the damage pattern, if you see the damage patterns, both in terms of civil infrastructure, both in terms of natural hazards like landslides, they are actually being controlled by what is happening some 30 kilometers below the surface. And that is the reason I'm trying to say that the first lesson we should get, that hydrologic extremes, in case of of this magnitude, the damage pattern is predictable because the geology is fixed in these time scales. We are not changing the geology in these time scales. When we are not changing the geology, so the damage zones are predictable. This is the first lesson. And over the years, when you see, these valleys are actually filled by so many, huge amount of sediment, and most of this sediment is actually the flood driven sediment. Poorly sorted clasts and the things like that. So over the years, over thousands of years, these floods have actually helped in developing the landscape, and that's where the terraces are formed. And roughly, if you see, if you map these flood deposits, around 3 into 10 power 10 tons of sediment is still logged in these river valleys. So the whole lot of terraces are formed because of these actually flood deposits, flood events. So what happened now? So this is something which I'll try to make. You see, this whole topography is so dynamic. This is 1930 image, and a famous duo of teacher and son, student Haim and Ganser, they are sitting on a lake bank. This lake was formed due to a major landslide which was occurred in around 1893. And it blocked a small tributary of Ganga called Birahi Ganga. And Birahi Ganga was blocked in 1893. And this famous duo, they are sitting there and having their lunch. So after around 1970, the same lake was breached, and you see the modern topography. So these kinds of events have huge potential of redistributing the sediment in a way that it will change the landscape for centuries together, right? And again, the same sediment is being transported to the foreland system. And in the time scales of 100,000 years, this sediment overloads the under thrusting plate so far so that the peripheral bulge gets uplifted. So in a way, I'm trying to say that in a smaller time scales, these events are developing, they are damaging the landscape. In longer time scales, they are building the topography. In further longer time scales, they are trying to modulate the foreland and thrust topography, actually, how the foreland will actually develop. So in different time scales, these kinds of floods have different contributions. So getting into the deeper, how important these floods are, how we should understand these floods. See, these are the humble sedimentary deposits. silt and clay capping. I mean, you see that coarser sand and they are capped by these siltier layers. So individual sand and silt couplet actually represents one flood event. And in the rising limb, during the rising limb of the flood, you actually deposit these sandier unit, and during the waning part of the flood, the clay caps are deposited. So you have one sand and capped by a clay unit. This one couplet represent one floods. So these kinds of deposits are called as slack water deposits, and they can be found in many places in Himalaya and can be mapped. And if we date these kinds of deposits, we'll be able to lay our hands on the recurrence intervals. If we do the sedimentology of the provenance analysis of these floods, we'll be able to lay our hands on where these floods actually erode and from where they bring the sediments and what are the forcing factors. And we will be able to understand a lot about the structure of the floods. In most cases, these flood deposits, I mean slack water deposits, they are found at the tributary junctions, major tributaries. I mean, this is Zanskar rivers, this is Indus River. At the junction of these two rivers, these kinds of tributaries are found. And at times, you'll also find these deposits hanging on the bedrock benches. And then where the rivers are actually, they have wider floodplains. And so, I mean, in most cases, these deposits will be found where you expect a sudden drop in the flood velocities. So these are the three common places in mountains where you can find the slack water deposits commonly. And another fortuitous things that we often recover from these flood deposits are these human hearths. Hearths are the places where when older prehistoric humans, they will sit and cook their food. And when they cook their food on grounds, it becomes hardened and reddened. So those reddened hearths, these are called as hearths, and they are the past camping grounds. And along those hearths, you will find often chewed bones, some stone flakes, and these cow dungs or yak dungs and things like that. And this is how they look like. So we come to know that these kinds of floodplains where these recurring flood deposits are preserved have been utilized by the prehistoric humans, and we can use these events, we can use these evidences to understand the flood and the human dynamics. So I'll start with two. I mean, as I told you in the very beginning, that I'll be speaking about the two major river systems. One is the Indus that flows from in the rain shadow zone and crisscrosses through the western syntaxis and joins in the plains of Pakistan and further joins to Arabian Sea. And then the second river I'll be talking about the extreme east. This is the Brahmaputra, Sangpo, and this river drains the southeastern Tibet and flows through the eastern syntaxis, and comes down and meets Ganga in Bangladesh. You see, this is the river catchment, and this is the trunk channel. And if you draw the longitudinal profiles of these two river systems and join them, because these rivers overlap each other, you'll find, I mean, that this whole Tibetan plateau on which these two catchments are lying is actually dipping towards the northeast. And this part operates in the rain shadow zone, whereas this part is in the reach of the flood, I mean, Indian summer monsoon. And you see that orography is playing very important role. And that is the reason in the northwestern part, you'll find that most of the Indus River system is actually desertic, whereas the southern part, whereas in southeastern part that is largely drained by Brahmaputra, has some kind of lakes that often breach. And this river experiences mega floods, large floods. And the reason why these lakes actually breach, it's that around the last glacial maxima or before that, this part of Tibetan plateau was completely it was covered by the glaciers. And when these glaciers retreated, you have a lot of glacial lakes in these areas. And because now it is at the lower elevation, and you have this area is within the reach of the Indian summer monsoon, these lakes are vulnerable to breach. And that is the reason the two river systems experience the floods that are very different in nature and in the magnitude. You see, these thin deposits, centimeter scale deposits, are the flood deposits of the Indus River system. And these 5 to 20 meter thick sequences, they are laid down by the flood in the Brahmaputra. So Brahmaputra experiences the flood that is orders of magnitude different than the Indus. And the reason being a continental scale topography. So first I told you about that the mountain scale or reach scale or the catchment scale topography of the mountain actually is controlling the damage pattern. And now the magnitude, I'm suggesting that it is basically controlled by the continental scale topography and how it interacts with the monsoon system. And that is the reason the floods in the Indus, they are of the orders of magnitude lower than what we see in the Brahmaputra. You can see these deposits. I mean, Brahmaputra deposits are 5 to 20 meters thick and they are massive sand, whereas in the Indus, you have sand silt clays, couplets, and they are centimeter thick only. So I'll talk about some of the flood deposits in Indus now. You see, this is the topography of the mountain from say in the Indus catchment, and this is the rainfall profile, and Indus River lies in the rain shadow zone. Ladakh, you see, this is the brown, I mean, this is sand ram. It almost looks like a cold desert. So this is the geology of Indus catchment in India, in Ladakh. This pink is the Ladakh granite or batholith, and in south of it you have brown, which is the Indus molasses, and then you have Tethyan belt, and this Tethyan belt and Indus molasses is being drained by northerly river, which is called as Zanskar River, and this river is that drains at the boundary of Indus molasses and the Ladakh batholith is Indus River. So there is opportunity because these two river systems are actually draining the entirely different lithologies, entirely different geology. If we try to understand the provenance, we can really understand which river is actually supplying how much of the sediment in case of flood events. So what we did, we actually did some flood deposit and studied flood deposits in the Zanskar. We studied flood deposits up in Indus, upstream of Indus Zanskar confluence, and few flood deposits from the downstream of Indus Zanskar confluence. This exercise was done to understand the contribution, relative contribution of the two river catchments in the dry zone of Himalaya, and of course the topography and other things. See, this is the first. I mean, this is the Indus River where Zanskar Indus meets. You have at the bank, you have these kinds of deposits preserved, and these are slack water deposits, and they are dated using the optically stimulated luminescence technique. And we also have one hearth which was dated using the carbon-14 AMS. And this topography, this thing can be mapped using any digital elevation models, but we did it using this DGPS. So we mapped the cross section of these flood deposits, and using simple Manning equations, we tried to estimate the flood discharge that relates to these flood deposits, and we found that average summer discharge during the modern floods is actually 6 times lower. I mean, the floods in the Holocene, early Holocene, were 6 times larger than the modern floods. So we could actually map the cross section, and using the flood deposit elevation, we and using simple Manning equations, we computed the discharge of the floods, and the flood deposits were dated, and that's how we came to know that the floods during the early Holocene were at least 6 to 7 times higher or larger in magnitude than the modern flood deposits, flood records of Indus. Likewise, what we did, these are the different flood deposits. You see, these are the flood layers, and individual layers were lithoid, and the flood deposits were numbered. So in the upper Zanskar, this is the one section that we could date using the carbon 14, and these carbon 14 dates are derived from those human hearths, presence were dated, and that's also helped us in building the chronology of these floods. So we found that at least 27 floods were occurred during the early Holocene in the Upper Zanskar. At least the Upper Zanskar archives 27 large floods in this area in early Holocene. And then we did something similar exercise in the Lower Zanskars. And all these fire places that are preserved, and these flood deposits are numbered. So these are the several sections that helped us in counting the floods and seeing the flood frequencies. And combining the two records in the Upper Zanskars and from the Lower Zanskars, we could understand that during the early Holocene, post-glacial Holocene warming, around 27 floods or 24 floods in the lower part. The similar number, you see, in Upper Zanskar, you have 27 flood preserved. In Lower Zanskar, you have 24 flood deposits, events preserved in the same time plane. So almost 20 to 24 flood events are preserved in the in the Zanskar catchment. Likewise, in the upper Indus, we could see that in Upper Indus, upstream of Indus and Zanskar confluence, you have 18 flood events preserved around the same time plane, in the same time, right? After the Indus and Zanskars confluence, the flood deposits are doubled. So events of floods are doubling when the Zanskar meets the Indus. That means most of the floods are actually being generated in the Zanskars. And Zanskar is the catchment. If you see, it actually rises from the higher Himalayan test line, and this part of the higher Himalayan test line is very much within the reach of the monsoon. So this is the unusual scenario where the headwaters of the river system, of any river system, are actually wetter than the lower reaches. And this is why we are seeing that Zanskars are providing more flood events than the Indus in the Indus catchment of the mountain area. So you see, if you put the dates in some kind of frequency distribution, these are the flood deposits, these are the flood frequencies, flood deposits of dated in Zanskars and Indus. And this second panel B, is actually the chronology of the human hearths, human fireplaces. And this is the record which was developed by a Chinese group, Shao et al. I forgot to mention here, I guess. Yeah, so it's a Shao et al. 2003 to 2021 or something like that. So you see, it's a Pangongso lake, and the lake record suggests that around 12 Ka, this whole Indus system started wettening or warming, and this lake level reaches up high, and the modern aridity is very young. It's around 2000 years old only. So the flood frequencies, you see, the flood phase 1 is actually occurring at around 14 to 12 Ka when the monsoon starts picking up, and then 10 to 8, and then third phase is 7 to 4 Ka. After this, the flood frequencies in Indus start declining, and that is very much is also replicated in the lake record of the Pangongso, which is in the vicinity. And another interesting thing to note is that the frequency of hearth is actually increasing. So in the Indus system, that lies in the rain shadow zone, is actually experiencing the inbound human migration when the flood frequencies are rising. When the post-glacial monsoon enhances or the warming occurs, the inbound human migration also occurs in the drier part of the Himalaya. This is what we could understand when we see the frequencies of human hearths and the flood frequencies using the slack water deposits chronology. And another interesting thing, when you compare these things with the southeastern monsoon or what is happening in the southeast China, this flood frequencies in the Brahmaputra or in the southeast China, I mean Yangtze and other places, you see these flood frequencies are increasing when the same thing is decreasing in Indus. So the Indus and the Brahmaputra system are actually operating as a seesaw when as far as flood frequencies are concerned. So there are three things which we could understand in this study: is the phases of warming and strengthened Indus summer monsoon induces the higher flood frequencies in the Indus system. Indus system experiences the inbound human migrations when the flood warming occurs. There exists an inverse relationship between the Indus system and the East Asian monsoon system. This is the second thing which we could, and we did some chronologies of the lake strands of Tangongso, and we found on the highest lake strand, which is dated to around 1700 years, and the lake was actually a freshwater lake because it was having mollusks which is a freshwater system. Radix is a freshwater gastropod that is preserved on the highest strand of the lake, and that highest strand is dated to around 1.6 thousand years. 1.6 Ka using the carbon 14 AMS, and subsequent to this lake dropped and the salinity actually came into picture. So the lake record is also suggesting that the aridity in Ladakh is very, very young. And in the southern front, the similar thing, we see that this is the lake record which we dated, and we found that monsoon actually picks up after the last glacial maxima, and it picks up, it peaks at around 13K or 8K or so. And this is why we are trying to understand that how the floods in Indus are very different than the floods in the Ganga system. We also did some provenance analysis of these flood deposits in Indus, and we found that most of the sediments, you see that the Indus system, this is largely Tethyan belt, and Tethyan belt is being intruded by the granite system, which is Pan-African in age, around 5 million years. Whereas the pink granites are 120 million years to around 70, 60 million years or so. So these two populations are very distinct populations. This is Upper Zanskars and this is Lower Zanskar. So when you see after the confluence, this Indus is being actually dominated by the population which is being supplied by the Zanskars. So as I said in the very beginning, that flood dynamics or flood frequency of Indus in the upper catchment is controlled by Zanskars, and likewise the sediment budget is also controlled by the upper Zanskars. You see, the 70% of the sediment contribution batholith reduces to 30% only after the Zanskar confluences. And this gives us another story to think of, that in the southern front, which is monsoon dominated, we all know that higher Himalayan crystalline, which is the core of the Himalaya, is being eroded. The similar thing is true for the drier part of the Himalaya also. This is what our study is suggesting, that most of the northerly flowing systems are actually having the wetter headwaters, and they are supplying large amount of sediment to in the system. And that's how even in the drier part of the Himalaya, the core of the Himalaya is being eroded effectively. Now let us talk a little bit about the Brahmaputra system. This is the Brahmaputra catchment, and this is how the topography, longitudinal rain profile looks like. This is the Tibetan Plateau part, and this is the Syntaxis, Tsangpo Gorge, and this is the southern front of the Brahmaputra. And this is, as I told you in the beginning, that flood deposits in Brahmaputra are very different than the Indus. If you see the litholag, they do not have those kinds of flood couplets. They are one shot around 2 meters around 4 meters, around 12 meters. You see 12 meters, and likewise. So 5 to 20-meter thick deposits are found in the Brahmaputra, and they are dated. And we could see that these sediment actually, when we did the sediment petrography, I mean, we prepared the sand slides and we did some petrology. We did some zircon chronology, and also this time we did strontium neodymium. And converging all these three techniques, we found that these floods are actually originating again on the Tibetan plateau. And it is exhuming a whole lot of sediment from the higher Himalayan crystallines. And that's how the floods are operating in this area. And the chronology is this, that around 4 Ka, I mean, when we actually mapped the flood cross section and we tried to understand the flood discharges, paleo discharges, we found that around 4 Ka, the discharge of the flood was of 10 power 6, 10 power 7 cumecs. So this 10 power 7 cumecs of the flood in Brahmaputra qualifies to be called as mega flood. And this mega flood occurred in the human time scales. 4 Ka, when the lower Harappans were living in those areas. So in the human time scales, a mega flood category flood occurred in the Brahmaputra, and the records of these floods are preserved in this valley. And the chronology and the flood deposits, the petrography and the zircon chronology and the isotopes do suggest these floods are originating in Tibetan plateau. They are exhuming a whole lot of sediment from the Indus, from the eastern syntaxis, and they are bringing the sediments to the Brahmaputra foreland. And one of my friends, he did some zircon fission track chronology on those zircons, and he found that during the normal floods, the exhumation, I mean, the erosion and the exhumation is of the order of only, say, 9 millimeter per year. And this changes, and during the extreme events, during the floods of, say, 4 Ka and 5 Ka, what we dated, these deposits, these floods actually exhume the higher Himalayan crystallines, which is 4 times higher in magnitude. So these floods in the Brahmaputra are really very effective in terms of landscape lowering, in terms of sediment generation, and these floods are of mega flood categories, and they bring huge amounts of sediment that change the landscape in downstream regions. So now, concluding, we feel that in the Indus River system, the flood deposits, the flood magnitudes are of the 10 to the power 4 cumecs, and they occur during the wetter phases of the Holocene, when human activity also increases there. And floods in the Brahmaputra are often of the mega flood categories. They originate in Tibetan plateau and exhume deeper rocks in the northeastern syntaxis. So you see, whole flood dynamics, flood damage, flood magnitude is being controlled by the catchment scale to continental scale geology, and how it interacts with, I mean, how these continental scale geology and the catchment scale geology interacts with the monsoon system. This is what actually decides the magnitude and the damage patterns of the floods. So it's basically the geology which has to be understood. And in the very beginning, I told that the large part of the global south is not having enough data flow. And that's probably is not helping them. And that's where the vulnerabilities are. So you see that built up this word cloud around the flood. No study is actually considering geology. You won't find geology in it. We are not understanding geology. We are trying to understand something which is controlled by geology. And that's where, and that too, when a whole lot of global south is not having enough empowerment, is not having enough of the data. So I'm really not sure how we will be able to handle these situations, especially when you see a recent publication in 2023, in July it came, when it is said that citizenship is determining the geoscientist's career. So it is everything. I mean, global south, you are not able to empower it, and you are not able to get the data. and we talk about the vulnerabilities. So the whole bottleneck is the data flow. The whole bottleneck is basically the empowerment, and that's where I believe major resources that actually build that are actually flowing in through the international community, like INCOA, Pages, IUGS, and your own group ProPrepare. I believe we have to assume the responsibility of empowering the global south, of bringing them on board and bringing large databases from these areas in order to build the models that are of global in nature. And this whole thing is being produced by all these young students that finished PhD while I was at Wardia Institute of Himalayan Geology. Thank you.